My name is Michael Alldritt, and I'm an analyst with Sydney Trains, and I'm completing a PhD at UTS. So this presentation is on using GNU radio in a multipath environment. So we'll just move on. So just an index basically showing what we're going to be discussing during the presentation. So moving on to an overview. So communication links can be created by modulating data on ultrasound, allowing information to be exchanged between devices. And sound propagates really well in liquids and solids, where traditional radio systems are attenuated. So for environments that you can't use a radio and RF doesn't work very well, modulated audio is an alternative solution. So transducers are used to basically convert the electrical energy to sound energy rather than to RF. So one of the project objectives basically is to allow high rail vehicles, which is road rail vehicles, to communicate with each other on the wayside when they are traveling in groups using ultrasound. So the transducers can be mounted on the track, and you can have another transducer in the cab. So you can have a device in the cab and it can communicate with the track, or you can have a device in the cab and it can communicate with another road rail vehicle in front or behind it. The rail wheels that actually go on the track are the means that the link is actually formed between the vehicle and the actual track itself. So how is this achieved, and what are the issues that need to be resolved? So the project uses a sound card as an analog to digital and digital to analog converter. And this is an alternative way of actually using GNU radio if you're not using an SDR. The audio frequency used is at 40 kilohertz, so we need to sample at more than twice that value as per the Nyquist theorem. And the sound card uses a sampling rate of 192 kilohertz, which is more than 4 times the value. So this allows a modulated ultrasound signal to be transmitted in the transmit transducer and demodulated in the receive transducer. So the issues encountered when trying to propagate in a dense material, such as steel, is as follows. The signal can take a number of different paths through the material arriving at different times, and the received signal has too many errors to be demodulated properly and the link fails. So in a normal radio, you only have a transverse wave, but in sound and in solids, you can have both a transverse and a longitude wave, or both. So you're having these issues not just with multiple transverse waves, but also multiple longitude waves. So it just complicates things a little bit. So what is multipath and echo? So when you look at just a normal multipath in audio, so you're looking at basically like the audio is reflecting off a hard surface, or it might be the actual boundary of the actual material, or even in water it might be like just areas where you have different densities, and that wave will actually bounce off and be reflected back. So as in the image there of the water, you can have like, you know, a direct transmission, or you can have it bouncing off the surface and coming back. So the receiver can get overwhelmed with all of these different pathways that the signal is arriving. So with wave interference, right, it can be caused by, it can either be constructive interference or destructive interference. So it can either reinforce the signal, or it can actually destroy the signal. So there's just something that you've got to actually be aware that, you know, it can be either a better signal or a worse signal, but with multipath, you won't get the right signal all the time. So what modulation techniques are available, and how well do they perform? So I've done some tests, and initially I was testing with binary frequency shift keying and flow graph and a sound card, and the FSK, the transmit and receive testing on a number of different substances. An image was modulated onto a data stream using ultrasonic transducers and transmitted through the substance. The baud rate that I was using was at 1200. And allowed the file to be sent in a reasonable time, which is about 5 to 10 minutes for a 70K file. The RX transducer picked up the received sound wave, which was demodulated in the software. And I got reasonably good results, so I was doing text and images and audio files through the actual substance. And I created a tank to basically hold the liquid if it was doing... so the tank used created a lot of reflected sound waves, and a cover was placed around the ORX transducer to limit the interference. I found that putting a shield over the transducer actually helped quite a bit. And some material failed, and I'll list it in the results slide a little bit further on. So this is kind of the setup that I was actually using, right? So I've got a sound card, and I've got an actual a tank. So I've basically put every sort of like substance I could think of into that tank. And on the in the image on the right hand side, we have blue laundry detergent, which I thought I'll try and see how I go with transmitting through that. And I did actually, with the tank, I did put a corrosive substance in, gas, and it did actually kind of destroy the tank, which was unusual. But anyway, I got through that one. So just moving on, this is the actual binary flow graph that I was actually using. Barry helped me with the actual post and preamble on this, which made it work. So if you're trying to actually have two devices and actually communicate with two devices, the post and preamble allowed the actual signal to synchronize, the receiver to synchronize with the transmitter, and you actually then got really good results. So again, this is showing the post and preamble, and you can see the actual the preamble there, I think, is to begin with, and then the actual data flow. Next one. So these were some of the images that I was actually using to actually transmit from one computer to another, and so they were at 70 kilobits. On this, I'm only showing one computer, but I've done this with a number, with two different computers located separately, so it does work when you're actually using separate devices. If I didn't have the post and preamble, it wouldn't work using this method. So these are some of the results that I got from actually using binary FSK. And obviously in water, well, you're not going to use this method for transmitting in air because you just use a radio. But for the other substances like water and petrol and diesel and milk, it actually worked quite well. And even down to some materials that were not so dense, like pine, I was still able to transmit like the actual image through the desk, which was made from pine, and I thought that was quite good. However, the what I wanted to transmit through was steel rail and hard material, and that failed. So I had to sort of think of another way of actually doing this. So in normal RF transmission, so what other solution can I use? And is OFDM a solution when FSK fails in a dense material? And the other question was, do I have enough bandwidth, right? Because the ultrasonic transducers have a cutoff point of 41 kilohertz on the upper side, upper part of the spectrum, and 39 kilohertz on the lower part of the spectrum. So you're working within a very small bandwidth, and you really need to have with OFDM, you need to have spectrum. You need to have like a spectrum for it to work, and I only had a little bit of spectrum. So in normal RF transmission, OFDM has been a great benefit to resolve the issues with signal ghosting from Multipath. Radio and TV reception has improved exponentially as a result, especially in locations where there are many structures that can block or reflect the signal. So some of us will remember, years ago, if we were picking up TV on the original, signal, and there was reflection, you'd get ghosting on the TV, and it could be very hard to watch anything because it was just the reception was so poor. So with OFDM, when that came along, right, and they went digital, a lot of these ghosting issues were resolved because of the brilliant way that OFDM works. The subcarriers used are very resilient and are not corrupted easily as opposed to the more traditional transmission protocols. And there are many applications using OFDM, like Wi-Fi, for example, uses OFDM, LTE, TV, DSL, ADSL and VDSL. They use the same structure with discrete multitone, so it works on telephone twisted pairs, which is quite good. The OFDM structure reduces the impact that multipath and crosstalk have on the transmitted data. So, next one. So we've confirmed that FSK is a great solution until we get to dense substances such as steel, rock, aluminium, and heavy plastics. And we know that tones can be heard in metals like rail in long distance. So a lot of people say, well, if you listen to a rail, you can actually hear the train coming, and it might be a long way away. And the reason for that is because the speed of sound propagates through rail 20 times faster than it does through air. And so the range is actually significantly further. So you can hear sound traveling through dense materials, not only a lot further, but also the signal does propagate further as well, yeah. So ultrasound, using ultrasound, it's above what people can hear in the normal audio range, so there's less interference at that range. There's less noise on the 40 kilohertz spectrum, which is great because you don't have interference from other things that we would normally be listening to. So OFDM is normally used in a broadband solution. Again, that's looking for bandwidth in megahertz, and I've got kilohertz, which is not good. And again, getting back to the transducers, the normal range for a normal ultrasonic transducer is about 1 kilohertz above or below the actual the spectrum, the 40 kilohertz, and it's just a design thing within the actual transducer itself. So you can't take it apart. There's no filtering or anything like that. It's so the actual solution was to try and get transducers with a bigger range, and that's what I did. I wanted transducers that had maybe 4 or 5 or maybe 8 kilohertz, but I managed to get one that had 3 or 4, and that was just enough to actually run the flow graph without breaking it. So this is just a great representation of OFDM, and you can see the subcarriers and the symbols, and it just shows the mechanism of the actual the channels, which I think is a very good graphical image. So next one. So to do the test, I was basically using a Ubuntu laptop with GNU radio. I do have Radio Conda loaded on my laptop, but the changing all the audio settings on my laptop was not something I wanted to do because it might not work after. So the USB sound card had a sampling rate of 192 kilohertz, so I set the sampling rate in pulse audio for 192 as well. The transducer had a bandwidth of 3 kilohertz center frequency, and at 40 kilohertz, and the steel track with attached transducers and audio plugs. The text test file to compare the output with the original, and I had an OFDM flow graph that was being used using a simulation config. And the flow graph I used, I found one that Quasem Chowdhury had actually modified before. I think he got it from somewhere else. And then I modified it again to actually work with my hardware. And this is the actual the graph. One of the things that's quite nice, because when you're using a sound card doesn't take a complex signal. So Quasem found this really great way of actually taking a complex signal and actually then bringing it back to a normal signal that could actually be fed into the microphone as a float, or into the speaker as a float, and then actually output it as to a sink, to a source as a float, to be able to be demodulated. So this actually worked for that, but if I could have got a SDR that worked at 40 kilohertz and accepted a complex signal, it would have made life so much better. And again, this is the receive, and again, we're using this method of taking the virtual source in and then actually combining it to get a complex where it can be taken into the rest of the flow graph to be demodulated. So this is roughly what my setup looked like. Again, I was just using a Ubuntu laptop Sound card, these are very good sound cards, and I went through so many different sound cards to get ones that actually did what they said they were supposed to do, which sampled at 192 and not at something else. And I basically have my microphone and my speaker connection. It's got an amplifier in it, which helped a lot. The ultrasonic transducers, these were really good transducers that I found. They had about 3 or 4 kilohertz of bandwidth, and they just held on the track with some Bluetooth, and that seemed to work and seemed to do the trick quite well. And this is 0.5 meter of 60 kg rail, which is standard rail that's used in railways all around the world, including the US. Yeah. So this is what the flow graph looked like. So just some screenshots from it. And you can see I'm getting everything that I need to, the constellation and the actual stem graph. So I was really pleased with that. And now this is a short video of the actual test. So I'm just going to play it. It goes for about 2 minutes, so it's not too long. So just showing the actual, when I started up, this is the rail, right, that I was using. And you'll see in the next second or two, it will show where the constellation comes in, which was very exciting at the time. So just there, you can see the constellation has come in, and then we're actually getting data into the actual, into the target file. And again, you can actually see we're at 40 kilohertz. And we've actually got we've got 3 kilohertz. We've set the actual variable at 3 kilohertz for our bandwidth. So just as it comes on, and so it didn't take too long. Now the reason I used a text file rather than something better, it just meant I could have the text file on repeat, and it meant if there was any issues or whatever, it would be repeating. So if there was a problem, if I did have an error, and then the second time it repeated, I wouldn't get that error again. So after I ran it for a little bit, I came in and I opened up the actual the test file. So I was using the Gettysburg address, one that Barry supplied, and I actually, and again, this is the actual transducers, and then I'll just open up the text file. So when I tried this previously with BFSK, it just did not work. It would work in air, but it would not work when I actually put the transducers onto the track. And I think I'm going to open up the file, which is, so there you go. So this is actually the target file, and you can actually see there's about 4 paragraphs, and I put line breaks then in between where it was repeating, and you can see it's actually repeated a number of times. So that was very exciting, and I was really thrilled when I could actually see that I was getting proper data flowing through the track. And I believe that the range I can probably get on this could be 30 to 50 meters, because I've done that with just tones previously. So I know that it could actually work for a range of about 30 to 50 meters. So I think that's kind of the end of that one. So that shows up. So again, this is just showing the actual source file and the target file, and the source file was basically the same as the target file. So it was really, and then so improvements that are planned. Okay, so the FSK flow graph had a pre and post amble, which I think will probably have to be added to this OFDM graph. I want to tweak the flow graph to see if I can reduce the bandwidth to lower, maybe 2 kilohertz if possible, without breaking it. And I also want to test it with images and audio files where when the flow graph is improved, and also testing with other dense materials like rock and other hard materials. I still have to do some testing on that, and basically tabulate the results from these improvements. And maybe the transducers, I don't have any shielding on the transducers, but that's something I want to actually put like a ground shielding on them. And finding a better transducers that have improved characteristics and performance. It was really hard to actually find a transducer that had any bandwidth. They were all, so I did find one that had a bigger range than 2 kilohertz, but they weren't easy to find. And yeah, so this kind of is where we're at, and I'd just like to thank everybody for their help and support. And I hope you've enjoyed the presentation, and if there's any questions or comments or anything like that, I'd be happy to answer them.
Transducers, I know the Navy uses very high frequency transducers like 2 megahertz or something.
Yeah.
I'm not sure if you tried any of those. And I guess the other comment, were any animals harmed during these experiments?
No. No, unfortunately. But look, transducers were a real challenge, trying to find transducers that had bandwidth. And yes, you're right, you can use it at a higher frequency, but I'm using a sound card, and the sound card basically had a 40 kilohertz. The maximum frequency I could go up to on the sound card was about 90 kilohertz. So I'd stay under the 192. I was trying to get a sound card that was actually had a higher sampling rate, but even the ones that were labeled, I got a couple from on eBay, and they said they were 384 kilohertz, and they weren't. When I looked at the chip, it said 96 kilohertz. So, Clayton.
Yeah, I'm curious what your what OFDM parameters you use. So how many carriers, and what your symbol rate was, and whether you needed to make any adjustments to those to get good performance, or if things just kind of worked with the flow graph you started with.
Yeah, like managing with the FSK, I had a mark and a space. It was binary. That was easy enough to resolve. But with the OFDM, I'm still a novice in many respects. And I was using the blocks that had been already developed, rather than being able to fully analyze and understand how they were actually working. But I know I was able to get it down to 3 kilohertz without breaking it.